Yes, so hello everyone. Welcome to today's session. So this is the third session being organized by this in our group Indian astronomers around the world. So today we are going to have an exciting talk about the Daksha, the upcoming space mission led by India, which especially and this talk is especially focused on the instrument capabilities of Daksha and the key science areas it helps us explore. So before we begin the talk. Uh, Today our speaker is Dr. Varun Balera. So a few words about him. He, yeah, so he works especially in the instrumentation part, especially the high energy astronomy, as well as these transients, especially related to compact object mergers. And he did his bachelor's at IIT Bombay, followed by MS and PhD at Caltech, and now and I guess this postdoc positions at IUCA, and now he's an associate professor at IIT Bombay, and he's also the principal investigator of this Daksha space mission. So, yeah, I would like to you to take over the session, Varun.
Thank you. Hi, all. It's a pleasure to meet all of you and e-meet all of you. So I'm going to start and I'm going to speak for about half an hour about Daksha. And if you have any questions, then feel free to ask them in between. If you type questions in the box, then somebody will have to repeat them for me. But the overall idea here is that I'm going to focus on the science and technical abilities of Daksha. And by studying all of that or discussing all of that, um, the hope is that you'll get excited about the science that this mission can actually enable. And then in the end, because this is largely a target group which has astronomers in it, the end goal is to see if any of you are interested in working in Daksha, how could you get involved? Okay, so to begin with, what is Daksha? So Daksha is a proposed Indian mission. It's led by IIT Bombay in close collaboration with PRL Ahmedabad, Raman Research Institute Bangalore, then IUCA in Pune, and various ISRO institutes. Okay, and right at the start here, I have a QR code for our website, which is just dakshasat.in. I'll give it that to you again in the end. So if you want any more details, including refereed papers or simple descriptions or whatever, then you can head over to the website. Okay, so right up front, what is the Daksha mission? So the mission is going to use a pair of satellites, two satellites on opposite sides of Earth, to continuously monitor the entire sky for high energy transients. So if there's one slide that you want to remember from this entire talk, then this is that slide. It's a mission that will continuously monitor the entire sky for high energy transients. Okay. So how do we do this and why do we do this? The genesis of the mission is, as Hemant introduced, my interest is in what is called EMGW, the study of electromagnetic counterparts to gravitational wave sources. So what you are seeing here is an artist's rendering of two neutron stars that are colliding with each other. And I'm going to play this again. This is a scientifically informed rendering of an event called GW170817. So looking at it from far away, we did not actually see this happen. All of this have appeared as a point source, but here is what we have reconstructed from that. So what you see here are two neutron stars, this, and they are orbiting each other. And then with these blue shading, what is denoted is gravitational waves being emitted from those neutron stars. Now, of course, gravitational waves like this are not made of light, they are waves in gravity. But this is just the artist rendering from that. You can see that there are distortions of background stars happening. And as they radiate energy to gravitational waves, they lose that energy, which means that the orbit shrinks, they come together and they collide. And when they collide, there's a massive explosion. It launches jets, highly relativistic jets, and a lot of crazy physics that we can never probe on Earth actually happens there. And this was an event that people had been wanting to study for decades. And we saw one case in 2017 where we saw gravitational waves from the source and we saw the electromagnetic radiation also from the source. And now that's almost a decade old, and we've been working very, very hard, but we have not seen anything. Why do we care about this event? So this event alone has generated more than 1,300 refereed papers about this over the years. Okay, and large number of scientific outcomes, very exciting things. This was the first confirmation ever that short gamma ray bursts actually come from neutron star mergers. It has proven to be an independent measure of H naught. So for those of you who are familiar with things like Hubble tension, this gives us a third independent measurement. This is also known to be the only site or the dominant site. It verified that this is the dominant site of R process nucleosynthesis in the universe, which means that this is where all the lanthanides and gold, silver, platinum, and bunch of these heavy elements are getting formed. And it gave us a measurement of the equation of state of neutron stars by being able to measure the gravitational wave waveform as well as the electromagnetic counterparts. And as I said, we've been looking very hard. I stopped updating this table in 2020 because it was very exciting to see that there was a merger that involved at least one neutron star. So a merger of either two neutron stars or a neutron star and a black hole that were detected by the gravitational wave detector network. And what is given here is the working name of that event, how far away it was, what was the area on the sky. And you can see that most of them are thousands or tens of thousands of square degrees, with the notable exception of this one. And then, assuming that the event is exactly like 170817, no model dependence, if you simply scale the fluxes, then how bright would they be in different bands? And you can see that with the exception of LSST, this is too faint for typical survey telescopes. Okay, with the exception of Rubin, most survey telescopes go down to about 21st magnitude. IR is again way too faint. Most IR surveys go to about 17th or 18th magnitude. And in X-ray and optical, these fluxes are in units of 10 raised to minus 7 ergs per centimeter square. And you can see that it is slightly fainter than that. Okay, sorry, this is in 10 raised to minus 8, but the typical sensitivities are few times 10 raised to minus 7. So situation is absolutely hopeless in optical. It is absolutely hopeless in IR, but this has gotten updated. There are new models which are a bit more optimistic, but it is only slightly hopeless in X-rays. It means that if you get X-ray telescopes which are a bit more sensitive than the current ones, then we can actually do better and we will be able to find these counterparts. And remember that one event has led to more than 1,000 refereed papers already and a lot of discoveries and lot of verifications that we had been waiting for a very long time. So how do you actually go ahead and achieve this? Okay, so my argument is that we want to observe in high energy, not in, you don't want to do searches in optical, you don't want to do searches in radio at all. And the reason for that is that the high energy emission actually comes on timescales of seconds after the merger, right? And then in minutes it goes to UV, hours in optical, it is days before it peaks in IR, and then the radio goes all the way to months. Okay, so the moment you are having a high energy telescope that is sensitive to these things, you actually get the fastest possible response of any band. And then the localizations, remember, were thousands of square degrees. You can easily bring them down to 100 square degrees with a good with a good X-ray telescope, something like say Fermi GBM, or ideally if you have even better localization, great. But if you can bring it down to about 100 square degrees, there are enough telescopes on the ground that can follow that up by now. In the northern hemisphere, the dominant one for this would be the Zwicky transient facility with a 42 square degree field of view. And in the south, you would have Rubin, which goes much deeper and over a 8 square degree field of view. Okay. There is also the main thing, which is that since we have been waiting for such a long time and we haven't found counterparts, it is questionable as to how much telescope time we can dedicate to a search if there is nothing that is to be found. But if we see that we saw a X-ray or a gamma ray counterpart, it means that the object has emitted light. And that tells you that you should be spending more time in following it up in other bands, right? If you go and discover something in IR 7 days after the merger, you cannot go back and look for high energy radiation because it's gone within seconds. And then finally, it also is a confirmation that there was a neutron star involved in the merger. And where does that matter? So if you look at the definition of the gravitational wave detector networks, then something that has a mass below 3 solar masses, they call it a neutron star. something that is above 5 solar masses is called a black hole, and in between this range is called the mass gap. And the reason is coming from optical and X-ray observations. We have seen neutron stars, the heaviest with small error bars is about 2.1 solar masses. The lightest black holes we know is about 5 solar masses, and from GR we know that neutron stars can't be heavier than about 3 solar masses. So if you have something that is in between this range, then was it a neutron star? Was it a black hole? Now, fundamental physics doesn't prevent black holes from being formed under this mass range. So we don't even know why there is a mass gap there. Okay. And then you have scenarios like this, where this object is sitting with error 6 plus minus plus 4 minus 2 is allowing it to fall in the mass gap. Or this one is a very tightly constrained mass, but is actually heavier than the heaviest neutron stars that we know. And there are many other such events that have also been seen. So the question is, what are these objects in the mass gap? And if you see it emit radiation, then that tells you it could not have been a black hole, right? There are some scenarios in which you can generate some signals from black hole mergers, but they usually involve timescales of months in generating transients from black hole mergers in AGN disks and so on. So if you see a transient, that tells you that a neutron star was involved. So that's going to be very interesting information about mass gap objects as well. So if all of this is so important, then who's really keeping watch? Turns out a lot of people are. Okay, so the dominant players in the game have long been Fermi and Swift. Then there's Integral and Astrosat, and GECAM and Swarm are the new instruments. Now, out of these, Fermi and Integral saw 170817. Swift and Astrosat were active, were sensitive enough to see this, but they did not see the event. It was Earth occulted for both of them. And GECAM and Swarm did not exist in 2017. They were launched later. Okay, so let's look at the astrosat scenario. Okay, so this band here is what the LIGO Hanford and LIGO Livingston localization of the source was. It was this green band and this green band here. Okay, the initial localization that came though was from a single detector, and that was essentially an all sky map. It was all over the place, which meant that early follow up was guided by Fermi GBM, which gave us this brown region over here. Now, Astrosat was active and it could see this part of the region. The white circle that you see here is the part of the sky that was hidden behind Earth as seen from Astrosat at that point of time. So from the very fact that we should have seen it and we didn't see it, we concluded that it must have been in this half of the sky. And indeed, eventually it was found here. So if you look at this close up, this is the image. And then here is this little point source sitting outside a galaxy, which was the counterpart. So what happens here is that any satellite in low Earth orbit that's orbiting at say 600 kilometers, Astrosat is 650, Fermi is 550, Swift is rapidly decaying right now, is at lower than 500 at this point. But the instantaneous sky coverage of any of these satellites is only about 70% at most. And then the duty cycle of a satellite, when it can remain active, is only about 70 to 75%. And the reason for that is that over Brazil and the South Atlantic Ocean, you have a region of tangled magnetic fields where charged particles come much closer to the Earth's surface. And if a satellite is passing through that, and all of these high energy satellites use high voltages, that can just cause shorting of the whole thing. So you don't want that, which means that during SAA passage, your instrument has to be disabled. So you are viewing 70% of the sky for about 70% of the time, which means that you have a 50-50 chance of seeing a random event in the sky. And that is consistent with what we actually saw here, that of the four sensitive instruments, two of them saw it and two did not. Okay, so if you now want to avoid this from happening again, what are the lessons learned? What would you do going forward? Well, the first thing is you want order of magnitude better chance of seeing it. And the term used for that is volumetric coverage. So given an event of a certain brightness, what is the volume of space over which you can find it, which means that you can make your telescope more sensitive so that you see further away. So you want large area, lower noise, and you also have to look wide, because if you're just seeing a narrow slice of the sky, then you will not see events that are elsewhere. So you want a very high field of view again. The second is that the flash is going to last only for seconds, and you don't have time to repoint the satellite. You can't get any further follow-up data. So you have to have a very wide spectral band, 1 keV to 1 MeV, so that you capture the full spectral signature. At the low end, you are going to see thermal components, signs of absorption. At the high end, you can see a cutoff that is happening, which tells you about the energetics of the jet that are involved. And finally, to ensure that you get the continuous coverage all sky, you actually want to put two satellites orbiting on opposite sides of Earth. And with this in mind is how we actually designed Daksha. Okay, so the instrument that you see here, there's a dome which actually sits right on top of this. Inside the dome are a bunch of detectors. This translucent box is what is called a satellite bus, and below that are detectors again. So at the low energy, these green strips that you see are renderings of silicon drift detectors, which will form our low energy detectors with the energy range from 1 to 30 keV. These are detectors that have legacy from Chandrayaan missions, from Chandrayaan 2 and 3. They have been working wonderfully. The workhorse, which gives us the main sensitivity, are cadmium zinc telluride detectors, which give us coverage from 20 to 200 keV. There are 13 packages on this dome shaped thing. So if you want a uniform all sky coverage, you would ideally think that you have to have a spherical detector. Turns out spherical satellite is not a great idea, but you can have a truncated sphere, so hemisphere. If you want to know the technical name for this, this is a truncated rhombi octocubohedron. 13 faces, so you have 8 faces in this ring over here. You have 4 diagonals and one at the top. And then to give you coverage on the lower side, we add 4 more sets of detectors. Each of these is called a medium energy package. So there are 13 packages here and 4 here at the bottom. And then the high energy packages can actually sit in the center here, because these highest energy photons of energies above 100 keV actually can penetrate into the satellite. So this is scintillators, just sodium iodide, and we have used them in multiple Indian missions. So everything is high technology readiness. These are evolutionary incremental developments on top of things that we have already done. And that is for de-risking. We don't want this to be a mission where technology demonstration is a purpose. The full goal is science, and we want to get to that as quickly as possible. And then, of course, there are 2 satellites, as I've already said, to give you continuous all sky coverage. If you want to compare it with your favorite satellites, then here is X-ray astronomers will be used to seeing these plots. You have effective area here, which is a comparison of sensitivity. So it's area multiplied by efficiency at that energy. And on the x-axis is energy going from 1 keV here to an MeV here. And your comparison, so the blue band is the low energy detectors of Daksha. This is medium, this is high. And you have multiple missions, Fermi, Swift, Swarm, HETI, and others, which are all plotted here for comparison. And this plot is showing the all sky coverage. While the black to yellow contrast looks very high, note that even in the worst place, we still have 950 square centimeters effective area. That's in these tiny points here. And the peak we get is about 1450 square centimeters. The all sky median for one satellite is 1300. Two combined, it doesn't double because they have different Earth occulted regions. So the median rises to about 1700 square centimeters. But this number is not indicative. So a burst will either get 1300 or directly 2600. Okay. If you want to compare them in terms of numbers, then again, this is from these are all refereed papers. I put archive numbers because they're easier to remember than a full ADS bib code. Um, Daksha compared with SwiftBat, Fermi, GECAM is the Chinese mission, Swarm is the French Chinese mission. Theseus, this is a previous iteration of Theseus. Every a couple of years, there's a newer iteration coming in. And there's a detailed comparison of the sensitivity of all of those. And the number that I told you to look for is what is the volume over which we can detect a 170817 like event. And you can see that Daksha, in terms of million cubic megaparsecs, is far, far higher than any of these other missions. Okay, it's a factor of 5 better than Fermi GBM, factor of 13 better than SwiftBat. So with all of this capacity, what will Daksha do? We have a large number of science cases. Let me quickly walk you through some of them, starting with relativistic transients. The I already talked about volumetric coverage for electromagnetic counterparts to gravitational wave sources. We will also be the key mission for gamma ray bursts. So this is the only mission that will give you ultra wide coverage for soft prompt emission. EP can do it for a fraction of the sky, but not for the full sky. And also it gives you a wideband 1 kV to 1 MeV on a single satellite platform, which means that we can work out the systematics extremely well and we can get really high sensitivity. Also, the detectors are being designed to have a microsecond time resolution, which means that this is the best for time resolved studies for bright GRBs, where the physics is varying on extremely rapid timescales. This is also going to be capable for highly capable instrument for GRB polarization. So let me go a bit more into that. So the first is EMGW. This is the paper where we did a whole bunch of simulations. We got together some theory experts from around the world, said what kind of model should we consider for electromagnetic counterparts to gravitational wave sources. We did full simulations, and what these bars show you is that if you consider a model with a jet and a cocoon, for example, then this is the number of off-axis GRBs that Daksha can detect. And then how many of them are also bright enough in gravitational waves to be seen by a 5 detector network, which includes LIGO India, or a 4 detector network that is up before LIGO India. And these bars show you those numbers. Now, the take home message is that no matter which shading or what you're looking at, Daksha is always higher than the current record holders, which is Fermi and Swift. Okay. What is more interesting though is that it enables us to look under the rug. So how do you define if something is a detection in gravitational waves, and you set a threshold saying that I want a certain false alarm rate that is based on me looking at the entire sky at all points of time. But if I can tell you precisely where to look and when to look, then I can actually reduce my search space, which means that my false alarm rate decreases drastically, which means I can lower my threshold. And back of the envelope calculation shows us that we can actually double the number of detections that we can get with this. And that's an incredible boost, right? You have all this expensive infrastructure being set up for gravitational wave detectors, and with a X-ray camera ray satellite, you can actually double that rate. And also, when we have this kind of sensitivity that is far higher than anything before, it opens up a huge discovery space. The universe is full of things that we have no idea about. And imagine the kind of discoveries that we can make when every single instrument here is downloading all photons at all times. So you can go back and look for your favorite objects post facto. You don't even need to know about it at that time. You could do stacking analysis, all sorts of things. Here's the example of GRB spectroscopy. Gamma ray bursts, for those of you who are from the field, are typically modeled with a phenomenological function called the band function. Okay, and what's happening is that within the explosion, within a time scale of tens of seconds, you are having this highly relativistic jet material moving with gamma factors of hundreds to thousands, and it is going to vary over time, but we often cannot have data that is good enough for fitting a physical model. Okay, so what we did was that we simulated spectrum with a physics-based model, saying that, okay, there's a power law, there's a high energy cutoff, and then we fit it with that phenomenological function, and you can see that when you subtract the model from data, you actually get residuals. You can see that this is not a good fit. So that's great. It means that for bright GRBs with fluence of about 5 times 10 raised to minus 5, we will be able to very cleanly see this difference. But not all GRBs are of this brightness. So let's actually take it down. I'm going to now animate this to make this a factor of 10 fainter. And you can see that the residuals are still obvious here. Okay, for those who are again from an X-ray background, if you go to the Daksha website, which is here, you can actually download response files, background files, and everything to do your own simulations. And we welcome all of that. There are also tutorials. We've conducted 2 workshops and Python notebooks, which allow you to download simulated Daksha data and do your own analysis, are all available there. I mentioned polarization. So the spectrum of GRBs, even if you can get a physics fit for bright GRBs, the spectrum is consistent with multiple models. But all of those models, so whether you are dominated by synchrotron emission or Compton scattering, whether you have organized ordered magnetic fields or random fields, all of them give distinct polarization signatures. And it's a nightmare to measure polarization in X-rays. Okay, so the current leader in this is actually AstroSat CZTI, which has the maximum number of GRB polarization measurements or constraints to be more precise. which is followed by a Chinese mission called Polar, which was a dedicated mission for measuring, but they have only upper limits. And Daksha will do better than both of them. Okay, so here are simulations that we did. The blue cross shows the measured value, and the red is what was injected. And you can see that these three sigma contours very nicely constrain the polarization angle and polarization fraction of these GRBs. So Daksha will also dominate in terms of polarization. Okay. So moving on from relativistic transients now, the next science case was compact objects. Anything that you can do for GRBs, you can also do for magnetar flares, for soft gamma repeaters. One of my PhD students is actually now doing a project jointly with IIT Indore, where we are searching for magnetar bursts that could be associated with FRBs and so on in astrosat data. And that's a pathfinder. And the next part that we are going to do is see what's the sensitivity of Daksha to these kind of events. Fast radio burst counterparts. We have seen a counterpart for only the galactic FRB. We want to see them further out, then you need a high sensitivity X-ray gamma ray spacecraft. So that's again the highest sensitivity of all satellites for this. We can also do nice things with accreting X-ray pulsars, which is that we can continuously time them for free. And that gives a immense advantage in getting continuous ephemeris of these things. And we'll do it better than VBM or BATSE. So here's what I'm talking about. Suppose you have something like a high mass X-ray binary or low mass X-ray binary. You have a companion star and then you have a neutron star that is accreting from that object. There may or may not be an accretion disk involved. But now what happens is that as you have accretion, you are releasing energy, and that is that matter that is falling on, the kinetic energy is getting converted into something which is finally giving you a luminosity in terms of radiation. It could be thermal, it could be non-thermal processes, whatever it is. But that same accretion is also carrying angular momentum, which means that you are going to change the spin of this neutron star. And if you study these systems, then they broadly end up falling into two classes. So these are slides from Biswajit Paul. So the first one is transient accreting X-ray pulsars. Okay, so what is plotted in the bottom panel here is its brightness versus time. So here you can see a large number of flares separated by small periods. The time axis is a bit small here, but this is 55,000 MJD and this is 56,000. So roughly this is 2,000 days across. And what you can see is on the top panel, you have the spin frequency in millihertz. So every time there is a bright accretion episode over here, you can see that the pulsar spins up. Okay, and that is because all the material that was going in was carrying angular momentum to the object. Sometimes it can spin down between these episodes. But the changes here are unpredictable. We don't know when a bright outburst is going to happen. Okay. On the other hand, you can have persistent accreting X-ray pulsars, and there you again see fluctuations in the intensity. You see changes in the spin periods, but they are not correlated at all. So we have no idea what is going on. And to do this properly, you need continuous data. So we simulated what can be done. So again, proof of concept was done with astrosat data. So what is shown here is crab pulsar, the pulse profile that is recovered from astrosat CZTI data when astrosat was pointing in some random direction. Okay, so this is when we were pointing at crab. This is when we were pointing somewhere else. And you can see that the profiles look the same. And then based on this, we took the sensitivity of Daksha into consideration. Here is what the data from Fermi GPM tells us for this particular system called GX301 minus 2. And way down here is the sensitivity of Daksha, which means this is extremely bright signals for Daksha. So we can see all of the Fermi GBM pulsars continuously, and we will be able to see a lot more. So that's another project which a postdoc of mine, Ashwin, who I believe is in the audience here today, is working on, saying that what can we do with Daksha for pulsars. Okay, moving on from compact objects, much closer to home, we can actually study the sun and the earth. So, for example, high altitude lightning gives something called terrestrial gamma ray flashes. This is pretty much an ideal mission for studying TGF. The only thing that's missing and that's technically not feasible in our design constraints is to have optical camera pointing down. But we will be able to measure all of these high altitude lightning discharges very well, and there are ground based networks that will collaborate with for that. This is the largest sun as a star. monitor that is ever built, much higher sensitivity than RESI. Another really cool idea that came up from community users, not from the core team, is actually monitoring the Earth's atmosphere. So what happens is if you have a solar flare, then that ionizes layers of the atmosphere, and these layers then fluoresce at their own characteristic energies. So we have again on a single platform a part which is pointing to the sun, that is measuring all the hard X-rays that we get. And then the soft X-ray part will be looking at the Earth at the same time. So we will be able to measure this fluorescence. And that allows you to do atmospheric profiling just by looking at solar flare data. And then various other science goals. For example, there's a nice paper published by Surud More, Priyanka Gowde, and me, which talks about how we can use gravitational lensing by primordial black holes. There's a window of about three orders of magnitude of asteroid mass primordial black holes that haven't been probed by any other method so far. That's because these black holes are so tiny. By the way, primordial black holes are hypothesis is one of the candidates for dark matter. Essentially, black holes could have been formed during the Big Bang or inflation or something like that. So these are so small in mass that their Schwarzschild radii are of the order of angstroms. So they are smaller than optical wavelengths. You need X-rays to probe even gravitational lensing around those. We will be able to study novae and slow transients. We will be able to get daily monitoring of persistent sources. Again, Ashwin and Tanishk and a few others in my group are working on a paper on this, and you should be able to see a paper in a couple of months on archive. So with all of these science cases, that's all there in our paper. If you want to take a look, what's the status of Daksha? We have what are called laboratory models ready for all three. So Daksha was proposed to ISRO in 2018. It was rated very highly based on the science. They gave us seed money. Then with additional funds from IIT Bombay and PRL, we went and developed lab models, proof of concepts, which work really well. So they match all the mission specs. Then we got delayed because of COVID. So post-COVID, things are getting back into order. We are currently in a phase where what ISRO calls study team. So the URSC has set up a study team which is evaluating the mission for technical and financial feasibility, and we are hoping that we'll get a decision within this calendar year. How does Daksha compare to other satellites around the world? So let's look at this. Fermi is a 16-year-old mission. It was not designed to live for so long. It was designed to have a 5 or extended 10-year mission, so it's much older. Swift is having serious problems. Right now, there is a rescue mission that is planned to boost the orbit of Swift. Hopefully, it works, but otherwise, that is an old platform, invaluable. Integral has already ended science operations. This is one of the youngest GRB missions, Astrosat, although it was not designed for GRBs. And then there are newer ones that have been launched. There is Swarm, GECAM, Einstein probe. But all of these have less sensitivity and less coverage as compared to Daksha. So EP, for example, is great for slower transients. But if you look at 1 second flashes, even in soft X-rays, Daksha actually has the same sensitivity as Einstein probe. This is the slide that I referred to at the start. So there are a lot of things that the core team is doing, but there are a lot of opportunities for doing other science or even hardware contributions from anyone who's interested. Two cool science ideas which have made it into our science cases by now: the search for primordial black holes and the profiling of the atmosphere were not things that were proposed by the core team. These were things that were proposed by the community based on the specs of Daksha. So if you are interested in things like this, here are a few ideas that we have put out on the science side. For example, we don't have theoretical models that have high enough fidelity that we could be able to fit them to Daksha data when it comes in. So how do you model time resolved components of GRB? If a GRB is postulated to have a black body component, can you write down the intensity and the temperature as a function of time? How do you interpret soft X-ray spectra of GRBs? What is the sensitivity and rates for various things? Simulations, TGF searches. If you want to do lab work, then there are scope for doing that. We'll help you with setting things up. We'll share all of our design details happily. So if you are interested, take a screenshot of this, or you can write to us later. We are also hiring at various levels, by the way. So if you are looking for a postdoc position or a staff position, we are looking for engineers in particular. We are looking for an electronics background person who could work with FPGAs. We are also hiring PhD students. Unfortunately, we do not have internship opportunities for undergrads or summer project opportunities at this point. We are looking for people who can engage in long term. We are also welcoming collaborators. So you don't have to move to one of the Daksha partner institutes. If your current position at your current institute allows you to take things up, if you want your group to get involved, write to me and I'll be happy to discuss that. So that brings me to half an hour. I'll leave you with this slide, and this is a good time to stop for questions.
Thank you for an excellent talk, Varun. So the session is open for questions. So you can raise your hand or write it in the chat if you have any questions.
Well, it means people understood everything or nothing.
Hmm. I think someone raised a hand.
Hello, sir.
I have a question.
Am I
Oh,
audible?
Okay, multiple people. So I see S. Mishra raised a hand first. So can you unmute and ask, please?
Hi, sir. Am I audible, sir?
Yes, you are.
Great. So, I am not from an astronomy background, but I do have a physics bachelor's. But I'm from the satellite side of things. I used to work on satellite bus. And what I am
Okay.
curious about is what are there any specific design decisions, or are there any specific advancements in satellite buses that you need for Daksha to perform to its specs?
So for Daksha, that's a great question. So for those who don't know satellite terminology, the primary satellite part as such is what is called the bus. So it has your antennas and solar panels and engines and communications gear and all of that pointing. And your scientific experiment is called the payload. Okay, so we are building the payload and we wanted this to be something that we can build fast, which means that we relied on having incremental developments rather than requiring any revolutionary changes. So from that perspective, we've designed this around what ISRO uses as a standard IMS-2 bus. So it's about a meter class satellite, and that's the bus that we will be using. The only change we need is that our power requirement is a bit higher. But other than that, this is a standard bus by choice.
Understood, sir. Thank you.
Okay, so I'll request the hosts to ask in order, name people in order in which they raise hands. I believe Rohan was trying to ask a question, but I don't know if he's raised his hand.
Let's. I can't see him
Uh,
here. Are you here?
yeah, I'm here. I
Sure.
wanted to know, I think someone in the chat already asked the question. I didn't see any science cases for supernova. So,
That is a great point. So what happens is that in case of Daksha, if you look at the base design that we have, okay, we actually, let's jump back to just the opening slide itself, right? So if you look at this design, what we are getting is there is no coded aperture mass, there is no imaging method here at all. We are just collecting photons from all directions at all times. So I could have just pointed behind me, this Daksha right here. What that means is that we are not sensitive to any slow varying things. So the shock breakout of a supernova is not quite bright enough. The sensitivity of Daksha is about 4 into 10 raised to minus 8 ergs per square centimeter per second in the medium energy X-ray band. That's not bright enough for supernovae. Or sorry, that's not sensitive enough for supernovae. Anything that varies on time scales longer than order of 1,000 seconds, it's very hard for us to see that. With novae, because they are so much closer, the brightest X-ray novae in the galaxies we should be able to see. But unfortunately, unless something really nearby, if there's a supernova in our own galaxy, everyone will see it. But
right.
by that, we won't be able to see anything.
Okay. Thank you.
I think Sahil raised hands first. So Sahil, you can go ahead and ask a question, please.
Okay. Thank you, sir, for the amazing talk. My
I'll
question
just
is
tell you,
specifically.
quickly also say where you are based and what you are doing? Are you a PhD student or what? Uh, so yes, back to you, Sahil.
Okay, so my name is Sahil. I'm a bachelor student at Somaya Vidya Vihar. I was an intern
Okay.
at IIT Bombay last year for 2 months at PSB, and yeah, I'm here for the talk because 2 years ago I was at IIT Bombay Tech Fest, and I for the first time I heard about Daksha there. So I've been following its progress. So thank you for the wonderful talk. My question is specifically regarding you mentioned that Daksha could help probe a new mass range for the theoretical primordial black holes, right? So
Yeah.
I wanted to know what is that hard feature or observational signature that would allow Daksha to distinguish a primordial black hole from say a common transient like GRB.
So here's what happens, okay? If you have, so the basics of gravitational lensing, if you have a background source and a heavy mass in between, then you see multiple images of that background source because light as it is traveling bends around that source. And in our case, instead of these two rays reaching the same point, we are looking at a scenario where we have one satellite here and one satellite here. So you would see different images of light going through different paths. The signature of the GRB will be identical. So it's the same GRB, but we will see slightly different intensities for that GRB in the two satellites. And we did detailed modeling of that, and that allowed us to figure out what is it that whether something is going to be a primordial black hole or not. Then we said that, okay, what's the number density of primordial black holes that you can put in that's consistent with current cosmological models and all of that. And it allowed us to say that if all of primordial black holes, all of dark matter is made up of primordial black holes, then we have a 50 to 80% chance of detecting it with an extended Daksha-like mission. Unfortunately, we are deep within Poisson statistics here. So if we don't see something, we can't rule out primordial black holes. And for that, we would need a mission that has one satellite in a moon-like distance from Earth, which takes our sensitivity much higher, allowing to do that. So for more details, I'll refer you to this paper.
Understood, sir. Thank you very much.
Alolika, would you like to go next?
Yeah, yes. Am I audible?
Yeah, you
Yes,
are.
Alok.
Yes. Sir, my question is like, given the large amount of data and noise in such missions, like what are the main challenges in reliably detecting transient events in real time?
So the beauty of Daksha is that we have a lot of, okay, so there are multiple things that we can do in detecting transients. The first thing is that we've been doing this for a long time. Okay, so the core team of Daksha is the core team of AstroSat CZTI as well. So we have a lot of lessons learned from AstroSat that we are using. And those are being applied across the spectrum. So from mission management, how do we store documents? How are our codes documented? Mission data format, everything is ready. Okay, and if you look at this design of Daksha back here, because we have all these surfaces at different angles, what it does is that any given GRB will shine on a bunch of surfaces but will not shine on others. So that allows us to monitor the background very well, and we can do what is called, what Fermi, for example, calls a coherent search. So if I see a GRB on, okay, let me go back to a slide here again. So let's say I detect a GRB on this face. I detect something that looks like a transient on this medium energy package. Then I
Mhm.
must see it in this or this one as well. If I see
Oh,
it only in this and not in these, then it's clearly a false positive. So a lot of checks
mhm.
like that can be done. And then of course we can do, so there will be what we just call OBI, onboard intelligence, which will actually detect this, and it will send out alerts in low latency to be able to communicate over GCNs essentially to the whole world. But we will also be downloading every single photon that Daksha detects. And Daksha is also being designed to have a much higher dynamic range than previous missions, which means that,
Okay.
for instance, a month ago, there was a bright burst which saturated AstroSat. So we can't do polarization measurements in that because we just lost data in saturation. So that high dynamic range will allow us to view these things without saturating.
Yes, sir. Okay, sir. Got it. Thank you, sir.
Second.
Siddharth,
Am I audible?
Yes.
get to.
I have few questions. Actually, I am from LIGO Scientific Collaboration Australia.
Mm-hmm.
I have worked in the gravitational wave group in Australia in Perth. So there I
Okay.
was working on the 80-meter setup. So when I
Mm-hmm.
was working there till for 2 years there, from 2011 to 2013, then the chances of detecting gravitational wave was very less. But gradually, when I returned back to India, I realized that people were working on it, and in 2015 they detected it, and 2016-17 announced it, and the prize also went. And this event happened in 2017. So
Mm-hmm.
just want to know, like, there are so many events of neutron stars, but why only one event has been detected yet? Because there are a lot of events, like there are so many neutron stars
This is
pair.
the reason, right? This is okay. First is you are mixing up number of neutron stars that are there with number of neutron star mergers that are there.
Okay.
The merger of neutron stars happens by emission of gravitational waves. The energy loss there is much lesser than the orbital energy. So your typical what the median time in giga years, not in mega years. Okay, so it's very hard to get neutron stars to merge. The volumetric rate estimates are still broadly consistent. But what's been happening is that we did indeed detect a large number of events, and this table is incomplete because after 2020, it just became too depressing to update this table. But they are so far off that they are too faint for current telescopes. So with Rubin going
Okay.
online, we hope that and that's why the community is taking this seriously enough that LIGO's O4 observing run just ended and O5 was scheduled to start much later. But a new interim run called IR1 has been planned for later this year because we want the gravitational wave detector networks and I'm part of LIGO as well. So we want these networks to work together with Rubin to increase the odds of detecting these kind of events. So 22nd magnitude, 24th magnitude is actually within the reach of Vera Rubin Observatory or LSST. So what's happened is that these events, the gravitational wave detectors measure amplitude of a source. So when the sensitivity of a detector doubles, you can see sources which are twice as far away. On the other hand, we measure intensity in all electromagnetic detectors. So when your sensitivity increases by a factor of 2, you can see only 1.4 times far away, square root of 2 times far away. So gravitational wave detectors took a lot of time to pick up speed, but after that, they quickly ran off ahead into the race. And if things like Cosmic Explorer and Einstein Telescope come in, then that's going to change things even more. One of my
Yeah, I have
collaborators,
one more
Sanjit
question.
Mitra, here is working. He and his student and I, we are working on a paper where we are quantifying the impact that LIGO India can have on this because it will actually decrease these localizations by 1 to 2 orders of magnitude. And that will drastically increase the odds of finding these events.
Just one more question I have. See, I have worked in Indian Institute of Astrophysics also, like
Mhm.
more than 1 year. And IUCA, I was a vacation student program student there. Then I have worked in Stanford University in the Gravity Probe B experiment. And then I got selected for doing the master's program from Australia. So
Mhm.
I'm also an electronics and instrumentation engineer from
Mhm.
Cochin University of Science and Technology. So it's
Is
a
there a
relatively
question?
good institute, and Department of Instrumentation is very famous
Siddharth,
there.
is there a question?
Yeah, yeah. So my question is, how can I send you? How can I join your group? Like if I'm interested.
So you send me a formal application with what background you have for a. We are accepting, as I said, applications for postdoc positions right now. If you have completed your PhD, if you have not completed a PhD, then the deadline for physics department PhD applications is also just around now, I think.
No
And if
PhD.
you
I think I will. I
uh,
won't be able to do because I'm already
if you
like
have an engineering
deviated from
background
that.
and are looking for an electronics job, we are currently looking for someone in expertise in FPGAs. If you have that, send me an email.
Okay. Okay.
Just one
All right.
question. Varun, how much time do you have for this question so that we can be like
I can wait for a little bit more. Sure.
excellent. Hema-
So who's next?
Yeah, Aditya, can you go ahead?
Hello, am I audible?
Yes.
Hello. Thank you for the wonderful talk. I'm currently a PhD student based at UW Milwaukee,
Okay.
and I mean part of the great gravitational wave data analysis team here. I'm currently working on EM informed gravitational wave counterpart searches, and
Okay.
so Um, my question was, I mean, largely the main two candidates, especially for GRBs right now, the main two
Hmm.
candidate telescopes, as you said, that I get my EM data from are Swift and Fermi. I was wondering how, especially with respect to localization, but also other parameters that help us catch the GW counterparts from the EM data. How will especially the style localization and maybe other parameters like be different, be better for from
So,
Daksha as opposed to these?
so the broad sensitivity of Daksha is far better than Swift or Fermi, which you can see from here. If you also want to look at the sensitivity directly, then in terms of effective area comparisons, Daksha gives you Swift bat like effective area, much higher than Fermi effective area. By the way, Fermi is down here. This is NAI and this is BGO. This one is BGO, sorry, and this is NAI. So much higher than that, and it gives it to you over the entire sky. Okay, so the rates are just going to shoot up quite drastically. The spectral coverage is more broadband. BAT cuts off at 150 kV. We can go to higher energies. We are also in discussion with some European colleagues to see if we can get loft detectors, which would actually bump this up by a factor of 10. So we would go up here, and that would increase our abilities in soft X-rays, and we might then put a coded aperture mask there. The time resolution is better than Fermi and BAT. We will also download all photons, which they don't always do. Um, what else? Broader spectral coverage, higher sensitivity, better time resolution. For a given GRB, so Fermi's sensitivity is few times 10 raised to minus 7, ours is few times 10 raised to minus 8, which means for a given GRB, we see a lot more photons, much higher SNR. So significantly better on all fronts. And if you want to look at the detailed comparison, I would recommend that you go and look at this paper. This is Soumyadeep Bhattacharjee, who's now a PhD student at Caltech, Smardika Banerjee, who's a postdoc in Europe, and this is the paper. So that's where you will find more details. And if you want to work on any simulations or if you need anything from us, we'll be happy to collaborate on those fronts. We have your standard F-tool compatibles, response files and backgrounds and everything. We even have a mission data simulator, by the way. So you can put in your favorite sources and see what Daksha would see.
Oh, the mission data simulator is on the website, I'm assuming.
Yeah, it should be there. If you can't find it, write to me.
Okay,
Okay,
yeah,
okay, let me correct that. We have not released the simulator itself, but we have released mock simulated data. And that is there on the website. If you look at the workshop link from the website, then you'll find the mock data and analysis notebooks there. The response files are all on the website.
I see. Okay, I have noted down the papers, and yeah, thank you so much for the talk.
Welcome.
Yep.
Yeah, so there's a question from Deepan. He can't use his mic, so his question is that how we can he be successfully engaged in this field of gravitational waves and black holes, the interdisciplinary research.
So, okay, I'm just scrolling and okay, you're a PG student in background in
Yes.
computer science. How can you successfully engage in this field? We do have a lot of cross-disciplinary students who join our project. So Smarnika Banerjee here, for example, started off as a student in energy science. We have had students from computer science, from electrical engineering, civil engineering, metallurgy and material sciences, energy sciences, and so on. So we have a chance for students of all backgrounds to get involved. The ways of involvement, as I said, is that unfortunately we do not have internship or summer student positions that are available. We have put a lot of material online. If you look at my website, which is Star Lab, if you look up Star Lab IIT Bombay, you will find material on that. My group is called the Space Technology and Astrophysics Research Lab, or the Star Lab. So I'm putting the link to Star Lab here. Star dash. Okay, just a minute. So you can look at our site if you want to do some self-study. Those resources are there. If you want to do a PhD, you can join us, or if you're already doing a PhD in some other institute, if your guides are okay with it, you could take up projects with us. Those are the ways to get involved. I hope that answers your question, Deep. Okay, there's a question in chat now that I'm looking at it from S. Mishra. Would both satellites be launched simultaneously on the same launch vehicle? Yes, we expect that both of them are mounted together with a dual launch adapter in a single PSLV and launched. That said, I would like to reiterate Daksha is still being evaluated. We are not a fully approved mission. We are being taken seriously, but we are not yet fully approved. So again, to answer Deepan's follow-up question, Deepan, doing research means joining a PhD program, right? Research is not something that you can do casually on the side, and there are a lot of places where you could join a PhD program. Okay, Arijita is asking in case of, okay, Deepan, yes, you'll find all the details on IIT Bombay's website. We take people from a lot of engineering backgrounds. Arijita's question about black holes. We don't get EM counterparts. There are some models that can actually create electromagnetic counterparts to black holes as well. For example, if the black hole has a small amount of residual charge, we expect astrophysical black holes to be neutral, but if there's a small amount of charge, that could generate a signal. Gaurav Varadkar has published a paper on upper limits and ruling out some models on the basis of that using AstroSat data. Incidentally, you are making me advertise here. So I've started a new series. If you follow my social media on either LinkedIn or Twitter or Facebook, every week I post a research paper from astronomy and astrophysics explained in simpler terms. It's still aimed at science students. It is not, so it is meant to be a shortcut. Think of it as a simplified version of Astrobytes for those of you who know what that is. I'm covering Gaurav's paper tomorrow morning. So in about 12 hours from now, you should be able to read a little story about what can we see about black holes. But largely speaking, no, black holes are black. So, and Daksha is looking for light. So Daksha will not see them unless any of these exotic models about emission from black hole mergers ends up being true. Rohan has his hand up again.
Rohan?
Yeah, if there's time, I could ask a quick question.
Yes,
Uh,
sure.
yeah. So you had mentioned that LSST might be able to come close to be able to monitor this. So given the timeline of the Daksha mission, are you working with like a alert stream that looks for these
So we
transients in
are
particular?
also, sure, go ahead, complete the question.
Look for these transients and maybe like a follow-up with Daksha
Yes,
or
so we
like
are
just
plugged
cross
into a
comparison.
lot of these things already. So we are also the group that jointly operates the Growth India telescope, for example, which is a robotic telescope. We are partners with ZTF. We have a letter of support from LSST, letter of support from ZTF saying that our transients they would look up. All the data is going to go public immediately, so anyone can do these searches. We'll plug into brokers. We have been using AstroSat for a test bed for all of these. So as we speak, um, people from the GCN team are talking to people from the Daksha team about how to integrate AstroSat into the interplanetary network and into GCN as a prototype and test bed because we are following the same data format. So we want to have all of these pipelines ready even before launch. And yeah, we can provide streams going into brokers and things like that. We are not directly part of the Rubin collaboration. Okay, so we will not be doing those searches, but there are other members of the Daksha collaboration in various Indian institutes and abroad who are part of Rubin. So they will have access to all of this. So yes, we will be doing these kind of things. I see two questions about the orbit. Going into a higher orbit actually has a lot of problems. So if you go into a lower orbit, you decay too quickly. That's the problem that Swift is facing right now. So you want low Earth orbit to be 600 plus kilometers. So we have assumed the astrosite-like orbit. Going exactly at a equatorial inclination is better, but it turns out that if you launch PSLV from the southernmost point of India and you don't want to kill people in the process, which means that if the rocket fails, it has to crash into the ocean. So the lowest inclination you can get is 6 degrees. If you try to get it flatter, there's a risk that something might crash into Indonesia, and we don't want that. So 6 degrees, 650 kilometers is the orbit that we have assumed. If you go higher, Earth occultation decreases, but the Earth's magnetic field no longer protects you from cosmic rays and solar wind and things like that. So your background goes up. So there are missions like Moonbeam and so on, which have been discussed in this context, where you go much further away from Earth, you get great sensitivity. Sorry, you get great coverage, but you have problems with how to download all of that data when you're that much further away, and you have problems with significantly higher background, and you're trying to find faint events, so you want your background to be low. So there are a lot of trade-offs that happen, but low Earth orbit is the one that we chose. In fact, ISRO asked us, why do you not want to launch to the moon or something? And we said, no, this is scientifically the best orbit for us.
If
There's a question from Shailaja Mate. When did the neutron stars collide? The event that we saw in 2017 was at about 40 megaparsecs, which means that they collided about 120 million years ago. And that light reached us in 2017.
I think we don't have any more questions in here. Okay, there is one. What is the complete timeline of completion of Daksha, like an year?
That is an excellent question. That does not really depend completely on us. Once we are approved, we can deliver the payload in 3 years, which means that we'll be able to launch in four. So if we get an approval of 20, in 2026, we could be looking at a launch in 2030. That's the development timeline that we are looking at, but approval for launch depends on a lot of different considerations. There are three other missions that are being considered. We don't know if one will be selected or all four will be selected or none will be selected. India is prioritizing human spaceflight program. So there are a lot of programmatic factors. We are scientifically very strong. We are technically very strong, but this is a policy decision which we don't know which way it will go.
So you're trying to be in parallel with LIGO India working conditions.
Yes, of course we are. Why not?
All right.
There's good overlap between the Daksha team and the LIGO India team.
Yeah. I have a question, but I'm not from high energy background. I'm like a very optical person and infrared at maximum. My question is related to the slides you showed about what are other science which can Daksha do in parallel. I wanted to understand if I hope Daksha goes in space and it's observing from two these positions, how these times will be distributed. Like it's going to monitor the sky for these transients entire time. So
Yes.
will there be a proposal, something which you can put to do other science, and how it is gonna work?
So, you've 2 years ago, this movie won an Oscar called Everything Everywhere All the Time. Right? That's what Daksha is. It's looking at everything everywhere at all times. It's continuously observing
Okay.
everywhere. There is no repointing involved in the mission at all. Okay, and the proposal that we have is that once we launch, we will have 6 months or 1 year of what is called a checkout period, where we want to tweak the spacecraft parameters, make sure everything is working fine. Every mission has that. Once the checkout period is over, everyone in the world will get the data at pretty much the same time. Okay, I might have a few minutes lead when I'm looking at the data first before sending it out. But the intent that we have, and again depends on policy approvals, but everyone will have access to data, and the tools for analyzing that data we have released already. Okay, and they are compatible with. So since you are saying optical, I would give an example of IRAF, and X-ray equivalent of IRAF is something called HEASOFT and XPEC and ISIS and things like that. So um, our data is being built to be compatible with those completely, which means that imagine, think of it as the alert stream from Vera Rubin Observatory. Okay, so Daksha will release not only an alert stream but also all data. So you can generate alerts that we missed. You can process the data, and alerts from the Daksha core team will fall in two categories. There will be low latency alerts from onboard processing, which will come with limited data, as happens with, let's say, Fermi right now. And then once the satellite flies over India, or we are also investigating other ground station contacts, once the satellite goes over here, we will get all the data and we will do detailed reprocessing. So we may find events that were missed earlier. We may reclassify events that the onboard software thought were real, but we now think they're spurious. We will improve localizations, we'll give more detailed spectra, we will have everything.
That's very interesting. That's very interesting science. Thank you so much for sharing.
Welcome. Thanks all. And I hope you have more shared excitement about Daksha at this point. And as I said, if you want to contribute to it scientifically, write to us and we'll be happy to talk.
Thank you so much, Varun. Thanks a lot.
Thank
People who
you.
can want to
Thank
talk
you so
about, they can send a message to Varun maybe, and
Yes.
they can find opportunities to talk about it. Thanks so much.
Thanks all. Bye.